Hello, everyone. My name is Haixin Shi. I'm very happy today to present our work. The topic of our work is free moving object reconstruction and post-estimation with virtual camera. This work was done during my master's thesis, co-supervised by EPFL CV Lab and MagiLib. First, let me show you the big picture of our work. So given a monocular RGB video for the free moving object and camera, and our task is to simultaneously just estimate the object poses and also generate the high quality object mesh. So this is very challenging task since we don't have priors. Most of the existing methods would have priors. For example, some of them may rely on the static scene, or they are limited to front-facing scenarios. Another direction of methods, they would just rely on the hand poses. They will use the hand poses to initialize the object poses. However, such methods would have strong priors that we need to grasp the object firmly. We could not just like use two hands to freely just rotate the object. Another recent SOTA, they just proposed that we can just segment the video sequence into multiple parts, and then we can optimize these passes independently. So they can just simplify the task, and then they can get some meaningful shapes. But we argue that this kind of solutions would just lead to local optimum. Different with the existing methods, we propose that we can do the whole task without segments, like we do the progressive optimization without segments, and we support the free moving object and free moving camera, so we can just generate very flexible application. And we can just generate the object mesh and also the object pose at the same time. Let me first introduce about the backbone of our system. We rely on a implicit neural rendering to optimize the pose and shape at the same time. So given a timestamp for a specific image, and then we can just estimate the camera to object pose. Based on this pose, we can set up a camera in the worst space, and then we can emit the rays to the world, and then we can sample the points on the ray. For this kind of points, we will input them into the SDF MLP. And the SDF MLP will output the SDF values and also the geometric features. Together with the X coordinates and also the view direction, we will input them into a color MLP. So we can predict the colors for all the sample points. Then we can do the volume rendering on all the points on a specific ray. So we can predict the color for all the pixels. So we can get the render image. We compare the render image with the ground truth image. Then we can calculate the loss, and then we can do the gradient backward. So we can supervise the whole system. We can learn the pose, the shape, and also the color together. However, only with the backbone is not enough. We still need the virtual camera to reduce the search space. How can we do that? First, we will use the out-of-shelf tool to estimate the object mask from the image. And then, based on this estimated mask, we can get the 2D bounding box, and then we can get the object center, right? So we can shift the object center to the image plane center. by a transform T. So here you can see all the images, the processed images, the object is always at the center. So we can imagine that there is a sequence of virtual cameras. They are always looking at the object center in the workspace. So you can see here. You can also imagine that the cameras are on a list of layers, the sphere layers. So the camera just walk around the sphere, and they always looking at the object center. So we only need 4 degrees of freedom to estimate the poses. 1 degree for the distance between the camera and the object, and 3 for the rotation for the camera around the object. So we don't need the standard 60 degree of freedom to depict the object pose. So we can reduce search space a lot. So the current question is that if we use the virtual camera, we can train the system. We get the pose and shape. How can we get the poses for the original image plane or the real camera system, the original camera? So the idea is that we can get the shape or the mesh, right? We can sample the points on the mesh, the 3D points. Our goal is to find the 2D correspondence in the real camera image plane. How can we do that? We first just project the 3D points onto the virtual image plane. So we can get some virtual 2D points. Then we can use the inverse matrix of the transform T that we recall earlier. Then we can transform these 2D points back to the real camera, like the real camera image plane, right? The projected points back to the real camera. So we can build up the 3D, 2D point correspondence between the mesh, the object space, and the original image plane. So we can use the PMP and RANSAC to get the poses for the real camera system. Then we can reboot the system, and then the task would be much easier, right? We only need to do the slight post refinement, and then we can start from scratch. That's the second stage of our method. We will do the global refinement. Only with the virtual camera is not enough. We still need the progressive optimization without segments. How can we do that? So first, let me explain the motivation. So if we only use one SDF MLP or color MLP, imagine that we want to reconstruct the hand, estimate the poses. So you would at the first few frames, you always look at this surface of the hand, right? You want to reconstruct it. And then your SDF network would overfit to this surface of the hand. So since you start from a unit sphere, right? So this surface may have very good shape, but on the back side, you may have very bad shapes. So whenever you just rotate the camera and look at the back side of the hand, you would be in trouble, right? So you since your SDF network would just give you very bad shape, you could not estimate the poses correctly. So our strategy is that wherever we just based on our post MLP's prediction, we detect a larger rotation. Like here, we go to the back side, we will reset the whole SDF network or just the color network. We will reset them to the original unit sphere. We will restart the optimization. But notice that here we would maintain the post MLP. We will keep them unchanged. So for example, when we are at the 100th image, right? You detect a larger rotation, you reset the whole system, but we will keep sampling the first 100 frames we've seen before. we saw before. So we can always use the previous well-learned frames to supervise the newly coming frames. So we have much better performance compared with other methods relying on segmenting the whole video sequence into multiple parts. Here is the visualization results on the public dataset HO3D dataset. So here we compare our method with the Hampley's method. So you can see here, since the Hampley's method, they just split the video sequence into multiple parts based on the object mask. So, and then they would do the multiple independent optimization. So they can generate bad results due to the local optimum. But we can deal with this kind of challenging sequence, even the textless objects, very well, since we do the progressive optimization without segments. Here, we collected another challenging data set, that is the egocentric data set with the Magic Leap 2, the AR glass. So you can see here, our method can generate very good poses and also very good shapes. However, the traditional algorithm, the BAF, they are also firstly just proposed that we can jointly optimize the pose and shape together, but this method didn't have a much special design. They could not deal with very challenging dynamic scenes. Here is the quantitative results for the pose, for the mesh, sorry. So for the first group, we compare with other pose-free methods. The code map is the traditional algorithm. They don't use the deep learning, and they just use the image feature, and then they can build up the 2D correspondence. So you can see that this method just fails in a lot of objects, especially the textureless picture or mark. The second method is the yes method. They just rely on the hand poses to initialize the object pose. And the third method is the Hampley, the recent SOTA, and it can have better results compared with the hand pose prior method. Notice that our method just have the best performance compared with this kind of three different types of pose-free methods. And the bottom group, they are strong baselines, since the Uniserve or the news, they have the GT pose to do the reconstruction. For the pattern, they have the GT depth. And our method has compared results with them. Here is the quantitative results for the pose. We also compare with the code map and Hampley, so our pose can be much accurate. And for the front pose and the mecha pose, they are the GT mesh based method. They use the render and compare strategy to estimate the object poses. Our method has much better results compared with them. The reason is that we observe that for this kind of 3D mesh-based pose estimators, they will have some outliers during the inference. So whenever we build up the whole trajectory, you can see that after the alignment, they will have very bad shift, and they are not very aligned with the GT trajectory. So they have very worse numbers. Here, we just show the effectiveness of our virtual camera. So here, the RC means that we would use the real camera to do the progressive optimization. So they can have very bad pose and bad mesh. With the virtual camera to reduce the search space, we can improve the performance. But after using the global refinement, we can get very close result with the Oracle one that is based on the GT pose. Here we also compare do the ablation study on different components of our method. So also about the match loss and the resetting mechanism we introduced earlier, and also the 4 degree of freedom that we don't use the 6 degree of freedom like the standard post-estimation. We can improve the performance. However, our method also has some limitations. For example, our method could not deal with the thin objects, or if the object is occluded by the hand for a long time, our method could not deal with it. Thank you very much for your attention. If you're interested in our work, please follow our project page and try our method. Thank you.